Mark. Good afternoon, everyone, and thank you for joining this webinar, an introduction to confidential computing. Today, we will look at different techniques for doing confidential computing. We'll also compare them in terms of maturity and look at the market offer before going through some conclusion and recommendation. But before we start, I'd like to look at the problem of secure remote computation. And first, computing on encrypted data. And in a very simplified way, if you look at your laptop today, most of us have encrypted data on the hard drive by default, and that's very useful if we lose our laptop. But at some point, we may want to do some useful things with these files. And so these files need to be loaded in the memory, decrypted, and then the processor can do something useful on these files. So that's what we see here on the storage, the file loaded into the memory. Decryption is done, some processing, and then we have the output, which is unencrypted and sent back to the hard drive after being encrypted. So that's in a very simple way what would happen on our laptops today when we want to work on sensitive data. It gets a bit more complicated if the data is on a remote system. So we know well how to encrypt the data on our hard drive. We know well how to encrypt it on the network when it's transferred between some remote infrastructure and our laptop. And on the remote infrastructure, we have something similar. We have computers over there. The data is encrypted in storage as before, but at some point where we want to do some computation or some processing on this data, we will need to decrypt this data for the machines, the remote machines, to be able to do something useful. So this is where things get a bit tricky, because after that decryption, first, well, where are the decryption keys stored? Who has access to them? And when the data is clear in the memory, couldn't there be some possible leaks to some other application or to some someone, an administrator watching what's going on? And that's where there are some concerns related to confidentiality, privacy, and the sovereignty of the data, especially when this data is stored on data centers which are not in Belgium, not even in Europe, and might be somewhere else. And that's where confidential computing comes into play to protect what we call data in use here while it is being processed. So we have data at rest on storage here, or even there in the data center. The data in move, in transfer on the network, and the data in use while it's being processed. And confidential computing addresses that last part, data in use. So there are three important techniques for confidential computing, and the aim is to try to move the infrastructure provider outside of the trust boundary. So one technique is called homomorphic encryption, and it's about, in fact, doing the processing on encrypted data itself. The second one is called secure multi-party computation. And here we will split the data in pieces and do some processing on the pieces individually and recombine the result. And the last one, where I will spend a bit more time, are called trusted execution environments. And there we leverage the strength of hardware security to provide some special mechanism to protect the data. So let's look at each of them in turn, and starting with homomorphic encryption. So as I said, with homomorphic encryption, we start with encrypted data, and in fact, this encrypted data is never decrypted. So here is an encrypted file on the client side. We send it to the remote infrastructure, and we send it together with a function f to evaluate on that data. So here we are in the remote infrastructure, which will apply a certain version of this S function in the encrypted space. So data remains encrypted here. We apply some specific variant of the function specific for the encrypted space, and then we return the results, which are still encrypted, and the client can decrypt the results to get the final or the desired result. Now, this function f can be more or less complex, and depending on the complexity of that function f, we talk about partial homomorphic encryption, if that function f is just about addition and subtractions, for instance. And we talk about fully homomorphic encryption when we can do addition, subtraction, multiplication, and division. And in between, we call that somewhat homomorphic encryption. And this is when we can only do a limited number of, let's say, multiplication and division, but unlimited number of addition and subtraction. And that really depends on the type of algorithm used behind. Now, let's have a look at a very simple example so that things become a bit clearer about what I just said. So let's assume that our client has three numbers, 7 and 3, which they wish to do some computation on, and that computation will be just the addition. We assume here that the encryption function is in fact just the multiplication by the key. So the input data, the input message M, is multiplied by the key K. And for the sake of this example, I'll use K equals 15. So when we encrypt 7 times 15 is 105, 3 times 15 is 45, and we have here now the encrypted data, 105 and 45, which we can send to the remote infrastructure, and it's still encrypted on encrypted storage. And at the same time or later, I set an instruction to do some operation, and here I choose addition. So the F in the previous slide is just the addition here. And the remote computer will then apply a specific function to the encrypted data. Now, it turns out that in this very simple example, what is an addition on the plain text, on the unencrypted data, is also an addition on the encrypted data. But for some other schemes, it could be different. There's a very popular encryption scheme, for instance, called Payek crypto system, and which converts an addition, for instance, in a multiplication in the encryption space. But in our example, we just need to add the encrypted value together. So 105.45 is 150, and we can return this encrypted result to the sender. And all they need to do is decrypt it, and the inverse operation of our encryption is the division by 15, and we end up with the expected result of 10. So I hope this clarify a bit what is hiding behind this homomorphic encryption. The algorithm in practice are, of course, much more complex than what I've just shown, but I hope it gives you a feeling of what happened. The important thing is that at no point the data is decrypted, and at no point the data in clear is accessible by any mean by the remote computer. So advantage is that, of course, as I just said, we compute directly on the encrypted data. The security of the system is based on very strong mathematical evidence under some well-defined and understood assumptions. We don't need specific hardware to be able to do that, and in fact, you can do some homomorphic encryption on your laptop today. And some of the schemes have the good idea to be robust to post-quantum attacks. Post-quantum attacks are something cryptographers talk a lot nowadays, and it's a good feature to have, of course. Homomorphic encryption is also an active area of research with regular improvements and new algorithms being presented, and so it's evolving quite fast. The not so positive things about homomorphic encryption is that it's not that easy to transform your existing application to take into account homomorphic encryption, and you will need the help of some expert cryptographer to help you built or rebuilt the protocols for your application based on homomorphic encryption. In addition to that, the homomorphic encryption schemes by themselves do not guarantee the computation. So in the previous example, the remote machine could have done a subtraction instead of an addition, and you wouldn't have been able to notice without doing the computation yourself. So you do need to add other types of mechanism to verify the computation done by homomorphic encryption. But these are, let's say, details compared to the more important issue, which is the overhead. The engineering cost overhead in terms of the complexity to parameterize the homomorphic encryption algorithm, and also the substantial changes that are required to existing applications. In addition to that, most homomorphic encryption schemes tend to blow up the data when encrypting. So some schemes, for instance, will transform 1 bit of information, plain text information, into 4096 bit of encrypted data. So that's a big overhead on the storage and on the bandwidth, the network bandwidth. Related to that, of course, is the relatively low performance of doing this kind of encryption decryption compared to other schemes that we use on a regular basis for electronic commerce, for instance. So now that was for homomorphic encryption. Let's look at multi-party computation, where we're going to split the data in pieces and have different parties doing some local computation. But first, let's look at a variant of a problem which inspired the idea of multi-party computation. And this variant is as follows. Suppose you have 3 computing companies who want to know which one of them has the lowest carbon footprint, and with the caveat that they do not want to reveal their respective values. So one option, of course, would be to use a trusted party, and each company would reveal their carbon footprint to that trusted party, who would then share the result. But a third party might be difficult to find, and also you're never too far away from possible corruption of that party. So the second solution, as you can imagine, is secure multi-party computation, which precisely enables mutually distrusting parties, such as these computing companies, to compute an arbitrary function on the input, and here the input being the carbon footprint value. Slightly more formally, suppose you have n parties, P1 to Pn, and each of them have a secret xi, so that's the input data, and they want to evaluate a function f on this data. And we want to do that in such a way that only the outcome of the computation, that is f applied to the xi, is learned by any of the party, and nothing else about the xi is learned by the parties. So one possible multi-party computation solution is to convert the function f into some arithmetic circuit basically in a composition of addition and multiplications, and then to follow a very specific protocol, which is as follows: that first, each party split the input data into pieces and share pieces with other parties, and then apply the additions and multiplication as specified by the f function to the local shares. And then there will be some protocol to recombine the partial results to get the final results. And as before, I'll show you a very simple example to illustrate how this may look like. And again, here we're going to do that on a simple addition. This time we have 3 parties, P1, P2, P3, and we want to compute the addition of their input values, so 7 plus 4 plus 10. So as I said, first step, is to split the data into pieces. And that's what we do here. And we're going to do it in a way that the sum of each piece is equal to the input data. So 2 plus 1 plus 4 is 7, 1 plus 0 plus 3 is 4, and 3 plus 2 plus 5 is 10 here. Next step is for each participant to share the pieces with other participants. So we're going to do this way. Each participant send one piece to another participant. So at the end of that sharing process, each participant has one piece from another participant. Next step is to do the local computation, and we're going to do a local addition. So each participant will compute the sum of their partial input. So 2 plus 1 plus 3 is 6, 1 plus 2 is 3, and 4 plus 3 plus 5 is 12. And so now we have three partial computation results, so 6, 3, and 12. Next step is to share these partial computation results with the other participants. And now we reach the state where each participant has a copy of each of the partial results. And the final step is for each participant to compute the sum of these partial results. 6 plus 3, 9, plus 12, 21, and 21 was the number we were expecting, 7 plus 4 plus 10. Note that in this process, at no point, any of the participant has access to the input of the others. So, for instance, participant P2 never knows the value 10 or the value 7. So that's the beauty here of this multi-party computation. One different way to look at the problem is the following, and we're going back to our initial state where we have our client with some data on which they want to do some processing. So they have the data they want to do some processing on, they split it in different shares, that's what we see here, and send a share to, for instance, different infrastructure provider. And these providers then start applying the algorithm I mentioned earlier to do the computation on the individual shares. And when they're done with that, they can return the partial result to the client. So that's what we have here, partial result on the first share, on the second share, and third share, and the client can recombine the result to get the final result of the computation. So that was it as a high-level view on multi-party computation. As I said, it enables the collaboration between interesting parties. That's a very nice advantage, and this has been used in real-life situations several years ago in Estonia, for instance, between the Ministry of Finance and the Ministry of Education. So these were two not fully trusting parties who wanted to do some interesting computation on their data, but without revealing their data to the other party. In particular, the financial institution, the tax institution, didn't want to share tax information with the education minister. The multi-party computation also does not require, as we've seen, and that's by construction, a central trusted party. That's a very nice feature to have. Just like also homomorphic encryption, it's based on strong cryptographic security, on some mathematical hard-to-solve problem, which makes it an advantage when you want to evaluate the security of such scheme. And you do not require special hardware, just like for homomorphic encryption. So you can do that with normal computers today. And again, a very active area of research, in particular at KU Leuven, where new schemes are coming regularly, and improved one as well. So that's an area which is changing rapidly. However, as you may have guessed, even from the very simple example I've shown earlier, these techniques are very complex, and as such, they're very difficult to verify formally, at least for the designers of those schemes. As users, they're also complex to set up and to manage. And just like for homomorphic encryption, they do require significant rewriting of existing application to be able to use them. Now, in addition to that, as you may have guessed from the example, there's a high level of communication between the parties who first need to exchange the shares of the input data, also need to exchange partial results. And in the example I've shown, it was just one addition. So you can imagine that for much more complex computation, the exchange of data is much higher. And this has, of course, an impact on the communication, the bandwidth, and the number of messages exchanged, which has also an impact on the time it takes to do the entire computation. There's also just a small number of applications in production. So I mentioned the case of Estonia. That was a live experiment, but today there are not that many real-life applications. It's mostly experiments with university institutions around the world. So the next and third, the third and last confidential computing techniques I wanted to talk about today, and we spend a little bit more time on that, are trusted execution environment. And here we're going to rely on the hardware. The goal is to better protect software processes from each other. And by software processes, I mean here not just a high-level application, but any process from driver to operating system to hypervisor from each other, by creating some isolated environment. And this environment this isolated environment is enforced by the hardware layer. The rationale being that the system cannot be secure if it's lower or lowest layers. Here, the hardware is not secure itself. There's a number of different requirements which are typically expected or imposed on trusted execution environment. First, that there should be a hardware root of trust to hold platform secrets which should be embedded within the hardware. There should be also reserved memory, which is encrypted for the code and data of your application or your virtual machine. And all input-output to the trusted execution environment should be encrypted. And the last important requirement is to be able to have some evidence that the system is authentic and its integrity has not been tampered with. So in a schematic way, if we look at a host machine today, on some remote infrastructure, you have here on this diagram, let's say the software part with two virtual machines, and within them application, operating system, and underneath supporting that the hypervisor. And underneath that, still you have all the hardware, the host computer with its processor, volatile memory, non-volatile memory, and other things. Now, today, potentially, all that is part of the surface attack at the first level of approximation. So a bad guy with access to the hardware could do a number of hardware-related attack, accessing directly the host. And on the software part, well, it could be an attack by the entity which controls the hypervisor, or it could be an application which gets compromised in one VM and then is able to go into another application through a number of attack techniques. The aim of the trusted execution environment is to reduce as much as possible to the minimum this attack surface. And in an ideal situation, that's what we want to have here, where The only areas where you would still be able to attack and get access to the plain data would be somewhere within the processor, which protects part of all or part of your application. And so you would end up in a situation where you have a kind of secure communication between your client directly with the secure part of your application, which is enforced by the secure processor. So that's the ideal situation, of course. And to be able to have this, first you need to also make sure that this entire system, that host computer, hasn't been tampered with and corresponds to what you expect. So how to do that? It's a bit like when you buy a new laptop in a shop. It's brand new, you come back home, you take it outside of the box, you turn it on, and you see your favorite operating system on it. And usually most people will start using it because they just bought it from the shop, it's brand new. However, if you buy it secondhand, well, you end up with the same laptop, at least it looks like it. You turn it on and you see the same operating system starting, and it just looks the same. So do you start using it, or what do you do? Do you clean the entire hard drive and reinstall the operating system? Well, that's what most security-minded people would do, because they are not sure of what's on that laptop. So it's a bit the same on the remote computers, on that infrastructure that we want to use. We first want to be sure that when we start talking to that or using the application on that remote computer, that computer is in a secure known state. And that's where mechanisms of secure boot are used on the remote infrastructure. And this mechanism first creates a chain of trust from the hardware. So the lowest level of the hardware, ideally secure chip or something within the microprocessor, to the BIOS, to the operating system, then to the application. And we want to ensure that each piece of firmware and software does correspond to what the lower level component, which is going to load it, expects. So that's secure boot, which allows us to reach a certain secure state, known secure state of the machine after it's been powered on. Now, that's not enough. We also want to make sure that the application that is going to be run within the trusted execution environment does correspond to the application we expect. We could have a well-trusted piece of hardware remotely, and we may upload our application, but someone might tamper with our application. So we want to be sure that it's really our application being executed. And that's where the mechanism of attestation is used. And an attestation is a signed evidence about the remote system and the state of the software running it. So it ensures that the system is the one we expect, and also that the binary within the protected environment is the one we expect. So typically, it would be, we would do a measurement of that binary, and that measurement, I'm using the term which is used in the confidential computing area, but in practice, it's a cryptographic hash of the binary, which we will sign with a certain key. And so let's have a look in more details at this attestation process, because I think it's very important in order to be able to verify that the remote system does correspond to what you expect. So on the left, you have your local trusted environment where you do your development. So you start with your source code, typically, you apply some compiler, and you end up with some kind of binary, which you're going to deploy on the remote infrastructure. And within the remote infrastructure, with the trusted execution environment technology, you're able to build that trusted execution environment in which you're going to put your binary. So that's the first step. But before using it, we want to be sure that that binary here does correspond to that binary here. And so at some point, we ask the system managing that trusted execution environment to give us a measurement of that binary and to sign it. And that makes the attestation, which is sent to us. So when we get it, we first verify the signature on the attestation. And so we download the required certificates for that. And when we follow the certificate chain, it should go to a trusted root certificate, which could be, which should be ideally the certificate of the hardware manufacturer, the microprocessor manufacturer. But it's not always the case today. And when we verify the signature, we can then compare what has been signed. So compare the hash which has been computed here with the hash which we can compute here. And if they match, then we know that the right software is running in that environment over there. With this mechanism, we can also set up some specific security policies and also establish encryption keys, which can then later be used to communicate securely between the application running in the secure environment and our local client. So in summary, for the trusted execution environment, we have hardware-based security, which can sometimes be better than software-based, but not always. But at least we do have that additional root of trust, which is really embedded in the microprocessor. And this allows us to trust the hardware manufacturer instead of the infrastructure provider. So as we'll see in practice later, this could allow us to not fully trust, for instance, AWS, but share the trust between AWS and AMD, for instance. These trusted execution environments supported by a microprocessor are available today from the main infrastructure providers. And they are relatively simple to use and to migrate application onto. And relatively simple compared to the two techniques we've seen earlier, multi-party computation and homomorphic encryption. Some vendors try to make it as easy as lift and shift of containers or of virtual machine. The not so good thing about or the disadvantages of trusted execution environment is that, well, by definition, they require specialized hardware. So you do need to use host computers which do have this hardware. Also, as I said, although the hardware security tends to be quite good, there's still some issues nowadays, and they are vulnerable to some specific physical attack and timing attacks, as revealed recently, in fact, by researchers at ETH Zurich, who did some research on the main processors used for TEs today. There's also potential risk with these techniques of having to use different abstractions from different vendors, and so potentially leading to a lock-in with that vendor. And the last issue, which I've noticed while working on that last year, is that it may not be possible to verify fully the attestation independently. So that was a quick overview also of trusted execution environment. Let's compare these three techniques: homomorphic encryption, multi-party computation, and trusted execution environment in terms of maturity. And here I'm going to rely on a report which was published last year by a group of experts who worked for the United Nations. So the report was ordered by the United Nations. On that graph here, you see on the x-axis the level of maturity. And the more you go to the right, the more mature is the technology. On the y-axis, it doesn't really matter. The report doesn't really explain what it means. And in fact, for the purpose of that illustration, we don't care. What's interesting here is that for all criteria, the trusted execution environment appear to be more mature than the two other techniques, except for one, which is having a sound theory of operation. As we've seen for homomorphic encryption and multi-party computation, we rely on well-known and understood cryptographic algorithm. But for all the other criteria, whether it's the functional system or benchmark suite or the IDs or others, according to that report, TEs are more mature. And this probably explain, well, maybe that's the chicken and egg problem, but why we see the TE widely deployed by current infrastructure providers. So let's look at the market offer now for these trusted execution environment. And first looking briefly at the manufacturer of microprocessors. So you have two main manufacturers catering for this type of computing. One is Intel and the other one AMD. The first one to offer trusted execution environment techniques was Intel with the Intel SGX for software guard extension technology. And the technique allows an application to fire some let's say, some routines in a secure environment. So within the flow of your existing application, at some point, you can call some specific function with the microprocessor who will then allocate for you a secure environment where you can execute predefined libraries. So you can imagine this at the time of development and compilation, a special library of your application would be designated to be able to run within a secure environment. And what the processor does is it allocates a specific area of the memory, encrypts that area of the memory, and ensures that only that specific library can process data on that protected memory, and no other process can access the data, not even the operating system or the hypervisor. When your library has finished processing, well, it returns to the normal flow of your existing application. So as you can imagine, this means that you have to redesign quite thoroughly your existing application to define exactly what will be able to run in the secure enclave. And enclave is a term which is used for that secure environment. And what's not. And what's in the secure enclave can process sensitive data. A different approach was proposed by AMD first, and it's with the secure encrypted virtualization and secure nested paging technology, SAV, SNP. And what AMD offers is a way to encrypt entire virtual machines. So the entire physical memory allocated to a specific virtual machine is encrypted with a key which is unique to that virtual machine and to the processor, which means that even if any other piece of software, whether it's the hypervisor or some firmware or some other operating system, can read physical memory, it won't be able to make any sense of it because it's encrypted for that specific virtual machine. Intel TDX for trusted domain extensions does something similar. It protects entire virtual machines. Here, it's of course much easier to develop applications because you can just, because the entire VMs is protected. And you have some variant also for Kubernetes and other types of containers. The disadvantage, of course, is that the amount of software running within the secure environment is much bigger, and therefore the attack surface much higher. But these are the two main techniques. And based on that, you have the infrastructure provider who offer different types of level of abstraction. So on the Azure system from Microsoft, you can use what they call application enclaves, which are based on the Intel SGX technology. So then you have to redefine your application and define, as I said earlier, what part of your application will be running in the secure environment and what part will not. You can also deploy what they call confidential VM, and that uses the AMD technology, but soon you'll be able to use also Intel TDX for that. And they also offer ways to deploy confidential Kubernetes containers based and underlying that is the Intel SGX technology. And their aim is to allow application developers to lift and shift their existing application. That's the aim. In terms of attestation, you can do that via the Microsoft Azure attestation system, but then your attestation is signed by Microsoft. So this means that you need to trust fully Microsoft here. Or you could use the AMD or Intel libraries, and so your attestation would then be signed by either a microprocessor manufacturer and not Microsoft. But in that case, you still need to include in your application some libraries which are proprietary of Microsoft. There's an additional cost, of course, for using this sort of techniques that you should be aware of. On AWS, it's of a different nature. AWS has been rolling out for the last since 2017, I believe, what's called the Nitro architecture, and more recently what's called the Nitro Enclave technology. But so the Nitro architecture rollout, basically what they did was to push anything related to the management of the virtual machines and of the network and of the storage out of the host computer, so that the processor of that host machine is only used for tasks of the customers. Everything else has been put on dedicated so-called Nitro cards, which are plugged in onto a fast PCI bus, and therefore separated at the physical level. So here you have in the gray part AWS software and management and hardware, etc. In the pink part, you have the host machine, which is a standard host dedicated solely, according to AWS, to the virtual machine of the customers. These virtual machine can be, from this virtual machine, you can carve out what's called a Nitro enclave, and that's what we see here on that VM on the right. Part of it has been cut out and given to a Nitro enclave. These Nitro enclave are just isolated virtual machines which run alongside what's called the parent virtual machine. They have no persistent storage, no network interface, no login access, and the only way for them to exchange data is via the some specific sockets, the old POSIX socket between the parent virtual machine and the Nitro enclave. So that complicates, of course, application development if you need to exchange data between that enclave and something outside across the internet. The use of the Nitro enclave doesn't bring any additional cost. Indeed, I mean, you just carve out part of your VM to run the enclave. So that's the Amazon solution. And last point I should say is that you can get an attestation from the AWS hypervisor, so signed by AWS, which tell you what's inside that enclave. Right. So let's now look at some conclusion and recommendation, and then I can take a question. Some general remarks. As we've seen, homomorphic encryption and multi-party computation are today not mature enough, and they remain limited to niche application. However, what we've seen is that trusted execution environment do provide some improved level of protection for computing infrastructures and application. And this is based on, as we've seen, a better process isolation enforced by the microprocessor, hardware memory encryption, secure boot techniques, and the remote attestation mechanism. In terms of market offer, from what I've seen during my study last year, Azure appears to offer the most varied solution based on Intel and AMD. AWS offer is, as we've seen, different in nature. You have the Nitro architecture and the Nitro enclave, which are not of the same kind as the Intel enclave. And there's also at AWS now a small offer based on AMD SCV-SMP technology. I didn't look in detail at Google's offer, but at the time I did the work, it appeared less mature than the offers from AWS and Microsoft, but they do provide some confidential computing technique based on AMD processor. Now, for all of them, the trust issue is not fully resolved. The client still needs to fully trust the infrastructure provider in practice. And this is because either the signature on your attestation is by the provider of the infrastructure, or because the code running inside, the binary running inside the enclave and signed through the attestation contains code from the infrastructure provider. There's a big question mark also about the overall performance impact due to the added complexity. So although for pure computation in the secure environment, there's almost no noticeable performance degradation, you have to take into account the rest of your application with the generation of keys, encryption and decryption keys, exchange with your KMS, and all the added complexity that you do need to put in place to ensure the security of the entire system. And this has some impact on the performance, impact which I haven't measured. Some recommendations, some of them are taken from recommendation of the Crossbank for social security, and I've put the link at the bottom of this slide. The link is to the Dutch version of the recommendation. So one first recommendation is about the attestation, and you should have the ability to verify the attestation independently from the infrastructure provider. If not, well, you should be aware of that and take the security measures accordingly. But ideally, the attestation should be signed by the hardware manufacturer. Related to that is the transparency. You should have the ability to verify the source code of any software used to operate the trusted execution environment. So this means any software running inside, but also the software outside helping enforce that environment. Software which could be firmware, by the way, if you really want to be sure of what's going on in the remote system. In addition to that, you should have the ability to at least import your own keys on your dedicated hardware. Ideally, you would want to manage your keys externally, but there's, of course, a latency issue related to that. And these techniques tend to be quite complex, either trusted execution environment, homomorphic encryption, or multi-party computation. So you will want to provide some training to your analysts, architects, and developers before jumping into that confidential computing world. And this will mean probably doing some POCs and other types of exercise like that before being able to port your existing applications. And the last point, last but not least, is to keep a holistic view on the security of the system. It's not because we've secured more or less data in use that the whole system is secure. So the entire security of the system needs to be studied carefully, especially in these public environments, which are extremely complex. So that's all I wanted to say today. So thanks very much for your attention, and I'm happy to take any question now. Thanks.